So today we're going to start talking about what happens when you have caching and multiple processors. So you may recall that at the end of Unit 2, we talked about other forms of parallelism. And in particular, we talked about how modern processors consist of multiple cores and sometimes even multiple threads within a core. And so you might remember this picture where we had individual cores. Cores had separate threads in them potentially. And we had certain caches that were per core and other caches that were shared between multiple cores. And then we also had entirely separate processors that shared the same memory, but had their own caches. So now that you've started studying caching, what we want to do is look at what happens when we have caching in the presence of multiprocessors, and in particular, what problems might arise. So what kinds of things could go wrong when we have multiple processors that share memory, but that have their own caches? So you might say, well, if they have their own caches, then it's possible that two separate cores or processors could read data and put that data in their cache, and now we have two copies. And the moment that you have two copies of something, you run the risk that they become inconsistent, right? Because let's imagine that core 1 wants to get some data, but it's dirty in core 2's cache. Well, that would be a problem. Or maybe processor 2 wants to read some data and it's dirty in the cache on processor 1, right? So it's not even on the same chip, it's on a completely separate chip. So the reality is that if the hardware doesn't do anything to avoid it, then cores and processors are going to see incorrect data. And as designers, it's our jobs to make sure that that doesn't happen. So let's look at this in a little more detail. So imagine that I have two processors here. And for now, we're just going to focus on the processor on the left that has two separate cores. So we have a value in memory called X, and we want to read it into core 1. So we're going to assume that we have a write allocate policy. And what that would mean is that when we read the memory, we're going to put it in the L2 cache and in the L1 cache. Okay, that's fine. Now let's assume that the core wants to write the data. So this is a write back cache. And so it's just going to change the value in the write back cache. So far, so good. But the question comes, now what happens when core 2 wants to read X? Well, it's in the L2 cache, which is shared. So the other core should just go read the data. But clearly that's not what we want, because now we've got a newer copy of the data in core 1's cache that is cafe, and we've got this old 1, 2, 3, 4 value that would get read into the cache on the second core. So that's clearly a problem. So even if we're just within a single core, if we don't do something clever, we have a problem. Now what happens if we're on separate cores? So let's say that the processor 1 and its first core is going to read X just like before. So we move it into the L2, and then we move it into the L1. Next, we're going to have processor 2 read that same value of X. So lo and behold, we copy it into the other L2, we copy it into the L1. Great, so far so good, no problems. But now what happens when processor 1, core 1, wants to write X? Well, now we write it there, and there's this stale data sitting in the other processor's cache, right? It's there, and again, unless we do something, we have a problem, okay? This is what we call an incoherent cache here, that bad things are going on. In reality, what we really want is we want hardware to prevent this kind of behavior. And so most processors are what are called cache coherent. And so if you were in the 11 o'clock section, you might remember that Sarita Adve did a lot of work in what are called memory models. And cache coherence protocols are in fact the mechanism that lets us actually implement some of these memory models. So typically it is the hardware's job to make sure that certain kinds of inconsistencies can't arise. And there's two parts to the solution, okay? One is that we have to make sure that the hardware enforces that when cores C loads, they actually get the last value that was written, right? Because that's the behavior we expect. Now, there are going to be some performance implications of that. And one of the reasons that we get into more complicated memory models is, in fact, to improve performance. But we're going to assume a world where we want every load or read to return the last value written. Okay, so that's our goal. And the hardware is going to ensure that. And we're going to have to add some more metadata to our cache to enable that to work. There are two general approaches that we use for this. One is called Snoopy caches, and the other is called directory-based coherence. So let's look at how Snoopy caches work. So the idea here is that you have some bus that all the caches can see. Okay, that's the fundamental assumption that you make when you want a Snoopy protocol. And so the idea is that if you see something go across the bus, then you can update your information, or you can send messages across that bus that other cores will pay attention to. Okay, so we're going to talk about invalidation protocols with snooping. So the idea is that as messages go across the bus, you can sort of peek at them and go, depending on what that message is, I know what I should do. Okay, so when a core writes a data item, all the other cores that have that data item need to sort of notice that and then invalidate their cache entries. So if we did that, what this would look like is that we're going to have core 1 read X again. So we do the same thing we did before. I'm simplifying this by ignoring the L2 cache for the moment. Okay, and now core 2 is going to read X. And again, so far, this is all great. Okay, but this time, when core 1 wants to write X, what it'll do is not only will it change the value, but it's going to send an invalidation message across the bus. And it's the responsibility of the second core to see that invalidation message and say, aha, what I need to do is invalidate my cache line. And so I'm going to evict it from my cache. Okay, so that's sort of what we want to happen. And the question is, what metadata do we need to support this? So we're going to enhance our cache metadata. So far, we've seen that we need things like the tags. Well, we still need tags, and we're going to need to check those tags to actually identify which invalidation messages we care about. We still need valid bits, and we still need dirty bits. But we're actually going to add one more state to our cache called a modified bit. Okay, well, actually, the modified bit really is the dirty bit. Sorry, we're going to add another state which says, this is a cache line that is shared among multiple caches. So I have a copy, and it is absolutely possible, and in fact, likely that somebody else has a copy too. And so we're going to introduce this new state because we have these three states called modified, which you can think of as dirty, shared, and invalid. We call this the MSI protocol. Okay, so these are the three states that a cache line can be in. So every cache line can be in one of these states. So here they are. And now, what state would you start in? When you boot your computer, what do you suppose the state is for all your cache lines? Well, unsurprisingly, you start in the invalid state. So what I'm going to do is I'm going to walk you through all the kinds of operations we might do, and we are going to derive the state diagram about how we move among these different states. Now, I know it's really tempting to just assume that you have to memorize this picture that we end up with. And instead, what I really want you to focus on is how we get there and why the transitions are as they are. So let's begin with the simple case. I have a cache line, it's in the invalid state, and on my processor, I want to do a read. So what do you suppose happens? If I do a local read, I'm going to get the data from the data source. And now what state do I go in? Well, the data is not dirty, so there's no reason for me to go to the modified state. So I will put it in the shared state because in particular, it's totally fine if somebody else has it in their cache in the shared state. So I'm going to go do a fetch from data. The other caches are going to see that, oh, you know, Margot's doing a fetch. And they might want to do something if they see that, but we'll come back to that later. Right now, I'm being very myopic from like my one processor. I did a read, I go in the shared state. Now, if I continue doing reads, I'm just going to stay in the shared state. Nothing changes. What happens if I now want to write that data? So we're assuming a write back cache. And we're assuming that the data is there because I'm in the shared state. So this is a write hit. Well, I'm about to modify the data. So I'm going to have to move into the modified state. Now, when I do that, two things happen. Okay, so I did a write, I go into the modified state. But remember, I was in a shared state. That means that some other processors might actually have the data. So it's my responsibility to send a message over the bus letting them know that, hey, I just wrote this data. So if you have it, you'd better invalidate. Okay, so I know they don't have it dirty because I would not be allowed to have it shared. So many of us might have had a copy. I'm about to write it. Everybody else has to invalidate. So I'm going to send that invalidate message. Okay. Now what happens if I'm in the modified state and I do some more reads and writes? Nothing. I can just stay in the modified state and life is good. Okay, so we did a read. We took a write hit where we had already done the read, the data was in our cache, and then we wrote. But what if we were in the invalid state? I'm sorry, clicker's not working. What if we were in the invalid state and now we got a write miss? So the data is not in the cache and I need to do a write. What happens? Well, it's a write, so I better go into the modified state. And again, I'm about to ask for data. So I'm going to go to the data source and ask for it. And when I ask for it, I'm going to tag it and say, and by the way, I'm going to modify it. Why am I going to do that? Because if I don't, all the other cores or processors that have this data in their cache might not know that they should invalidate the data. But in fact, since I'm going into the modified state and I'm going to write this data, they need to invalidate their data too. So I'm going to go out to the memory system and say, I need this data and I'm going to write it. Okay. All right, so those are all the things that can like operate on data in my cache. What else can happen? Well, what happens when my cache fills up and I need to evict a line? So let's assume that I am in the modified state. I have dirty data in my cache and now I want to evict. Well, if I'm evicting, we know that we're moving back to an invalid state. But before I do that, I'd better write that data back, because if I don't write the data back, I've lost the data. And that doesn't matter whether you're on a multiprocessor or a uniprocessor, you better write dirty data back before you evict. Okay, we can also evict from the shared state, right? In exactly the same way, which is that I'm in the shared state, I evict. This time, I don't really need to send any messages because the only thing that could happen is other people have it in the shared state. I don't have anything to write back. It's just a personal decision on my part that I no longer have this data. Finally, let's talk about what happens when your core, right, is the recipient of one of these messages, right? When I look at the bus and say, uh-oh, somebody's doing something to a cache line that I actually have in my cache, what is my reaction? So let's imagine that we're in the modified state. And what I see is that some other remote core is either trying to read or write this cache line. Okay, so I'm a core, I have a dirty cache line, and some other core either wants to read or write it. What must I do? Well, it turns out that what I must do is I must evict it. And so just like before, when I did a write back with an eviction, I'm also going to do a write back and eviction when I see any kind of remote read or write request. Okay, so the first case, I evicted it because my cache was full. I needed to reuse the cache line. This case, maybe my cache isn't full. I don't need the cache line, but I just saw a message indicating that some other core is about to read or write this data. And before they do that, I better get my writes out there so they see them, and I also better remove it from my cache. Similarly, I could have been in the shared state. And if I were in the shared state, if I see somebody else read the data, that's fine. But if I see that somebody else wants to write the data, then all of a sudden, the data in my cache is going to be dirty, stale, and I don't want it there. so I'm going to evict it or mark it invalid. Okay, I know that was a lot. It went by pretty quickly. Fortunately, you can replay this as many times as you want. And again, don't just try to memorize the picture. Think about the operations that can happen on the local core, and then what other cores might be doing that would force me to update my state.